This is the first video in section 3.6 on the gradient and the directional derivative. The goal of this section is to understand the gradient vector, the directional derivative, and the relationship between them, and to use the gradient to solve some geometric problems. So we'll start with section 3.6.1 on the gradient with definition 3.6.1. The gradient vector, or just gradient, of a function of x1 to xn at a point a1 through an is defined as the gradient of f at a1 through an it's a vector, f sub x1 of a1 through an as the first component, f sub x2 a1 through an as the second component, all the way up to f sub xn of a1 through an as the last component. So it is a vector, the vector of partials of the function f evaluated at the point a1 through an. When these partials exist, if one or more of the partials of f does not exist at a1 through an, then the gradient does not exist at a1 through an. A couple of notes here. The upside down triangle symbol is actually called nabla, but no one says that name out loud. Instead, this is read the gradient of f, or sometimes del f. The gradient is sometimes written without the vector symbol. So instead of this little vector up here, some people just write it without, and some people write it in words grad f. Let's do example 3.6.1. If f of x is the square root of x squared plus y squared, we're going to find the gradient of f at the point 3, 4 and sketch the surface with the gradient, and then find some places where the gradient does not exist. So the gradients of f at any point xy is the vector f sub x of xy and f sub y of xy. So that means we need to take the partial derivatives here, and so using the chain rule, we're going to have x over the square root of x squared plus y squared. So there were 2's in both of these places that got canceled out, and also the y component, y over the square root of x squared plus y squared. That's the gradient vector at any point xy. If we want the gradient at 3, 4, well, we're going to plug in 3, 4, and so that's going to be 3 over the square root of 3 squared plus 4 squared, which is 5, and 4 over 5. So there's the gradient at 3, 4. Now, what does it represent geometrically? Let's sketch the surface and where the gradient fits in this picture. So the surface f of xy is the top half of, if you square both sides, z squared is equal to x squared plus y squared, which is the double cone. So we have the top half of a double cone, which makes it the single cone facing upwards at the origin. So let's sketch that in. Give ourselves a nice big wide cone here. Now, actually add some axes first. There's the x, the y, and the z axis, and maybe give this a little bit of shading. So there's the top half of our cone. Now, our input point is 3, 4, which, as we've done a bunch of times, we will put as if it were the point 3, 4, 0. So there's our input point 3, 4. And the gradient, you will notice, right, we're in three-dimensional space. We've got x, y, and z, but the gradient also only has 2 components. So that means that I am going to draw it as if it were 3/5, 4/5, 0. It's not, but I'm going to draw it the same way that I drew 3, 4. I'm going to embed it in the x, y, z space. I'm going to embed it by putting it in the xy plane here. So there's our gradients on the point 3, 4. There's the gradient of f. And so we can imagine these Right, the image of the point 3,4 might be a point up on the surface there, and the image of the gradient as well. The image of the gradients couldn't be drawn on the surface, and that is something that will be important for us in a later section to imagine where the gradient is pointing as if we were standing on the surface. If we were actually to stand on that surface and follow the gradient, where would it lead us? So that's something that we're going to be exploring in a later section. The part B, so this was part A, part B asks us, are there places where the gradient does not exist? So the gradient does not exist. Well, if we take a look at the formulas for the gradient, we can't divide by 0. And we'll be dividing by 0 exactly when xy is 0, 0 at the origin. So our gradient does not exist at the origin, and if we take a look at the graph, what's happening at the origin? We have a sharp point. So that is something else that is going to be of use in later sections. When the gradient does not exist, we'll be wanting to examine those kinds of places to find maxima and minima of functions in a later section. So takeaway 12 here is just making the point this gradient being in the input vectors, in the input variable space. So the gradient, even though we're drawing in 3-dimensional space our surface, the gradient is in 2-dimensional space. It's in the space of the input variables. There's 2 variables, x and y, and the gradient has 2 components.